Hi guys, welcome to Learn Electronics Repair. Today's video is sponsored by PCBWay.com and we are going to look at a power supply project. I have some PCBs here. These are part of the shared project section on PCBWay, which I'll show you in a moment. These are projects uploaded by users of PCBWay's website, and the author of these projects, if you decide to build them and order the PCBs, will get a 10% commission from the sales. So yourself, if you want to design some projects and upload them, this is a great way to make some extra money without having to stock your own PCBs and worry about posting them out and all the other hard work that's involved. Really, you can upload your designs to here and there's no risk involved. Here we are on PCBWay.com. The shared project section you will find here. So we simply click on this and you will find thousands of projects on here, all different categories organized for you. Or you can just search for something if you're looking for something specific and see if anybody has uploaded this type of project. If not, why not design your own? We can look through all the projects and there are new ones being uploaded every day on here. But we can also use a search, so we're going to look for the 30 volt 10 amp power supply. That should do, 30V 0-10A, search. And this is the project which I built previously, we're going to look at now, and today we're going to make some modifications to this, we're going to improve this. Here we have the power supply. You'll see there's a YouTube video. This is actually in Turkish language, but you can watch it. This is the original author of this project. We have the specifications of the power supply and an example build. Now, you will see that this guy is using a very large toroidal transformer. These are quite expensive. You may be able to salvage one out of an old amplifier or something similar, but they are an expensive piece of kit, together with the large bridge rectifier, the large capacitor. The rest of the components on the PCB, this is the one that we are building, are quite inexpensive. So really the main expense of this project and similar ones is the power supply. I like to find cheap ways to do things to make this accessible to as many people as possible. So I'm not using a transformer like this one. I'm going to use something that's very cheap, very easily available, very high current output, and that is ATX power supplies. Let's look at the schematic for the power supply project. And here we have it. So if we take a look around this power supply, you will see there are 5 output transistors. That's these large transistors. These are the transistors that are regulating the output voltage. You can see, if we take a quick look, we have the transformer that the author used with 2 15 volt windings. He has them connected in series, giving a total of 30 volts. And there is a relay here, which if you look is actually switching between 15 volt winding or the two together, which is 30 volts. We also have a rectifier diode, smoothing capacitor, 18 volt Zener, so we have a voltage supply here. This is V+, this powers the chips that run our power supply. You can see here V+, V+, also this IC, V+. So this circuitry is permanently running from the 15 volt supply. The reason we have an 18 volt Zener here, well, it will act as a limit if for some reason you get voltage spikes, but also probably with a 15 volt transformer AC, by the time you've rectified it and smoothed it and you're not drawing much power from it, which this circuitry isn't, you'll probably get 18 volts or so here anyway. That's the peak voltage. This is the RMS voltage. The circuitry is quite simple. If you look, you have a bridge rectifier, some more large smoothing capacitors feeding into these transistors, this bank of transistors. The reason we have these is to share the power. So this can provide up to 10 amps. We actually send 2 amps through each transistor, put them onto a large heatsink, spread them out a little bit, and that's how we get the power rating. This is the output voltage you can see here. And this circuitry is driven by this chip. This is an LM723 voltage regulator chip. You can adjust the voltage here. It drives the transistor, the BC547B, which drives this one, this Darlington, which drives the output. So basically we vary the voltage here, and that varies the voltage on the output at much higher current. This section, this is the current limit. If you look at this voltage regulator, you'll see what it is doing. This is your output, voltage out and ground. But ground here is not the same as chassis ground, which is this ground, which we see on our chips. So in actual fact, we are monitoring the voltage drop across this bank of power resistors. There are 6 of them, 0.33 ohms each. They're all in parallel. As current flows through here to our true ground, and you'll notice to see that is true ground, that's the ground on the bridge rectifier, okay? So all the current through the load also flows through here and generates a voltage across these resistors. This regulator is actually monitoring the voltage there from this point, dividing it with some resistors, and it's comparing the voltage with the one on this adjustment. So basically, when the voltage here, which is set by the current here, matches the voltage set here, this will switch. And the output from this voltage regulator does 2 things. It lights this LED current limit, and it also sends a voltage signal back to this regulator, which reduces the output. It will continue to reduce the output until the voltage across here matches what you have set here. And that's how the current limit works. This is very sensitive. We can limit the current to a few milliamps and anywhere up to 10 amps smoothly. This power supply has another very clever trick, and this is what makes it very efficient. Normally with a power supply, if you are sending a low voltage to the load at high current, say for example you have a 5 volt load at 10 amps, okay? Coming in here, if you had one transformer with say 30 volts on, what do you have? You have 5 volts at 10 amps across your load, that's 50 watts, and you have the other 25 volts at 10 amps across your transistors, that's 250 watts. So these transistors are getting extremely hot, dissipating the excess energy to make sure you have the right voltage on your load. Now, the problem becomes worse the larger the difference between the output voltage and the input voltage. So what this power supply does, it monitors from here, you can see it, output voltage, via this resistor, and this variable resistor puts a voltage on this op amp. The higher the output voltage, the higher the voltage here. On the other input to the op amp, we have another voltage. Now this is the 18 volts. We have 2 resistors, 27k, 12k. So we will get here a bit less than half of the 18, about 9 volts on here. So we adjust this potentiometer to put 9 volts on here when we have, let's say, 13 volts on the output. Because to go above 13 volts, we need more input. And what that does, Luke, once the inverting input on the op amp goes above the voltage on the non-inverting input, the op amp will switch on. It will turn this transistor on. That turns this relay on. And the relay switches the contact. So we set this to trigger at say 13 volts out. It will now switch the input voltage up to 30. Okay? But we already have 13 on the output. So 30 minus 13 is about 17. This now dissipates about 170 watts maximum. And that's why it's done. When we're on lower voltage on the output, we have a lower voltage on the input. So that's how this circuit actually works. Now we understand that, we need to modify this to use our ATX power supplies. The ATX power supply, we're going to use the 12 volt output on each one, and we're going to use 2 of them. But this trick I'm going to show you a little bit later. We can use, for example, 3 and get up to 36 volts out of our power supply at 10 amps. But for now, let's look at modifying the ATX power supplies so we can connect two of them in series and switch the voltage with this relay. Again, when that's working, we'll look at a better way to do this. So instead of switching the relay, we can actually switch the second ATX power supply on using the green wire, the power supply on wire. That's what we're going to do today. Let's have a look. Here is the power supply I built a few videos ago. I will link the video from this one so you can see this being built and how we set it up and tested it. This is working just fine. We have the current setting here. We have the voltage setting. We have a coarse and fine voltage setting. We can add a fine current setting as well, so we can have coarse and fine on both. We will do that on the final version. And my prototype at the moment is only using one transistor. On the final version, we will have 5 of these in parallel, but this is perfectly fine for testing purposes. So this power supply can provide about 2 amps or so at the moment. It's on quite a large heatsink, as you can see, so the transistor won't get too hot while we're testing it. At the moment, we have a 12 volt light bulb on the output just soldered on. It's a 22 watts, so this draws a bit less than 2 amps with 12 volts input. And this is the relay. So the power in, and if we just move some wires out of the way, you'll see it says here in. This is your 0 volts in, or ground if you like. Here is the relay, and you can see the yellow wire goes to the other in, and the relay can switch between the red and violet wires. So this is how it switches between 15 volts input and 30 volts input. Now we're going to use ATX power supplies, so we're actually going to use 12 and 24 volt input. But to do that, we need to connect two ATX power supplies in series. Now, you may be wondering, can we connect switch mode power supplies in series to give us a higher voltage output? Yeah, we can. I'll show you that. We'll try first with 2 wall warts or little power packs. We'll put 2 in series. We'll see how that looks. And then we'll look at some extra factors we need to take into consideration when we do this with ATX power supplies. It's not quite so simple, but we can do it. Here we have 2 power supplies. This one is a 12 volt 1 amp. This one is a 12 volt half amp, 500 milliamp. We can connect these in series to get 24 volts, or for that matter, plus or minus 12, okay? You don't have to use 2 power supplies of the same voltage or the same current to do this. The only proviso is that if we connect these 2 in series, the maximum current we can get out of it is 0.5 of an amp, okay? Let's test our power supplies to see if they work, and then let's connect them in series. So we'll try this one. We have the wire, let's see what we get. So this should be giving us 12 volts. Okay, yep, 12 volts. The white one, what do we have? 12 volts. So they're both working. Now let's connect them in series. To do this, I've simply connected the power supplies into 2 sockets. The green crocodile clip lead is connecting the positive output of this power supply to the negative or ground of the other one. So if we take a look on this one, you will see we have 12 volts. And if we go from this one to the output of the other one, you will see we have 24 volts, okay? Also, this will teach you something else, which is a very basic thing, but some people don't quite get it. The fact that negative voltages don't really exist. It's all referenced or relevant, okay? So here we have plus 24 volts coming from our power supply. But if we connect the ground lead or the black lead of our meter to this is the one that joins the 2 together. We call this our ground lead. this power supply has plus 12 volts coming out of it. And the other one has minus 12, okay? I'll just draw that. It's so simple, and yet it's something that you really need to just get your head around. What are we doing then? Well, we have two switch mode power supplies. And we have 12 volts from each one. So the first one we have 0 volts and plus 12 volts, and we're connecting the plus 12 volts of this one to the 0 volts of the other one, and then again we have plus 12 volts. And that's what we have. Now, if we connect our black meter probe to here, so we call this ground, this point will have 12 volts on, and this point will have 24 volts on. And I've just shown that it has 24 volts on. How did I get plus and minus 12 volts out of two positive 12 volt supplies? Well, I connected my black meter lead, or if you like, the ground point, to here. Okay? When I measured to this point, I now have plus 12 volts. And when I measure to this point, I have minus 12 volts. So you can see positive and negative voltages don't really exist. All you have is a potential difference between one point and another. And depending where you consider to be your ground, you will see a positive or a negative voltage in this case, because this point is 12 volts less than this point. But we only see it as negative when our black meter lead is here. Like so. When we connect our black meter lead to here, we see plus 12, plus 24. So that's what we've done. Now, what would happen if we turn either one of the power supplies off? Will we get any voltage out of it? Will we get 12 volts out of it? Well, let's take a look. So at the moment, the black one is plugged in. So if we look at the white one, which is not plugged in, we have no voltage there. Let's look at the black one. Well, that's giving us 12 volts. So we have 12 volts coming out of this one. What's the voltage across the whole thing from one end to the other? Well, we go from ground on this one. This is the one that's switched off, to output on this one, and we have 12 volts. So with this one switched off and this one on, we get 12 volts. What happens if we plug this one in and unplug that one? Well, let's see. So the white one is now plugged in. And this one now has 12 volts. This one is now not plugged in. What do we have? Well, we have a little bit of voltage because the capacitors in this one are discharging since I unplugged it. But you can see it's going down to 0 volts. Okay, if we just leave it a moment, we get to 0. What do we have across the entire thing? So we go from ground on this one, the one that's switched on, to the output of this one, the one that isn't switched on. And we get 12 volts. Now, why do you think that is? Well, let me show you this. What you have in the power supplies basically is the secondary of the switch mode power supply transformer. So on the first one, we'll call this ground. We have our transformer secondary, and then this goes to a Schottky diode which feeds the output. Yes, there's some big smoothing capacitors here as well, okay? And what we're doing is we're connecting the output from this one, the 12 volts, as we showed before, to this one, the 0 volts, yeah? And then we have the transformer in here again, the diode, and the 12 volts coming out. So, as I showed, when we connect our meter positive to here, and we have ground on here, we get 24 volts. So, basically the ground of this power supply is at 12 volts already. This is holding it up to 12 volts, and then this adds 12 more. That's why we get 24. What happens when we switch one of the power supplies off? Well, if we switch this one off, then this inductor coil becomes, as far as the DC 12 volts coming out of here is concerned, just a piece of wire. It's a short. So the 12 volts from this one just goes straight through our piece of wire. It's not got high frequency AC on anymore. This is switched off through the other diode, and we still get 12 volts here. In actual fact, we get slightly less because there's a small voltage drop in this diode. But if these are Schottky diodes, it's probably about 0.15 volts drop. Okay. Surprisingly, what happens when we have this one on and this one off? Well, now effectively from our black meter lead here, we have through a piece of wire, this is no longer oscillating, through a diode to here is just effectively not exactly a short because the diode's there, but there's a small voltage drop. Okay. And then this point now is effectively not quite at 0 volts, it's about 0.15 volts because of that voltage drop. And then this one's running, so it adds 12 volts to that, and it gives us, well, maybe 12.15 volts. But really, you won't get 12.15 volts here. This is the sort of circuit that can be confusing to beginners, which is why I highlighted the fact. So, look at it again. This point here is 0 volts. Here, okay, and this point here with the one power supply on is 12 volts. So if we connect our meter probes here into our multimeter, we're going to see 12 volts. Okay, when we move the black lead down to here, so we're now measuring from here to here. Okay. What we've actually got is the voltage drop in the path. You need to look at it like this. This will make it more clear to you. So what we really have is, we have a voltage source, 12 volts. And this is connected via a diode, this one, to our multimeter. And our multimeter is basically a resistor, okay? Very high value, but it passes a tiny bit of current. That's how it actually measures the voltage. And our multimeter, ignoring the fact this is just a piece of wire when this power supply is off, so it's just a piece of wire, in fact we'll draw it as a piece of wire, is connected like that, okay? So that's actually the circuit we have. Now, you should be able to see that when we effectively get a voltage across the resistor, this is our meter, we've got two diodes in the path. This is exactly the same thing as if I drew it this way. Okay, if I drew it this way. And this will look more obvious. Okay, 12 volts. Now I'm sure here you can see that the voltage across this resistor is that voltage less two diode voltage drops. So if these were Schottky diodes, they're 0.15 each, this would give us about 0.3 volts drop. Yeah, if they were normal diodes, about 0.5 of a voltage, this would give us about 1 volt drop. So assuming normal diodes, what we would see here is 11 volts. Okay, this is exactly the same. We just have 1 voltage drop on this side of the resistor. Let's use normal diodes, half a volt. We have half a volt on this side. So you're still going to see 11 volts here. Sometimes you'll find these sort of things in circuits and schematics, and they're a little bit hard to get your head around sometimes. Just like PNP transistors with all those negative voltages on the base, which are not really negative. They're just reference to ground, yeah? So if you find things like this and then you redraw the equivalent, you will obviously see what the circuit's doing. Okay, back to the main show. So that's why with just one power supply on and one off, either of them, we still get 12 volts at the output. Hope you can see that. The $6,000 question then. Can we do this with ATX power supplies? Yes, but What's the problem with doing this with ATX power supplies then? Well, the problem is that this ground can't be connected to this ground, otherwise effectively this power supply will be shorted out on the 12 volt output. Now let's have a look at some ATX power supplies and see if this is an issue. Here we have two ATX power supplies, different makes, different ratings. So this one's 19 amp at 12 volt. This is 16 amp at 12 volt, which would mean if we use these, the maximum current we can draw is 16 amps. But we're actually only going to be drawing up to 10 anyway, so that isn't a problem. What could be a problem is the grounding. Let's check them. This power supply first. This is a 24 pin ATX. So we have ground, one of the black wires, and that connects to the case. Okay, so this case is ground. Let's look at the other one. This is actually a 20 pin, but it doesn't matter because we only want the ground, 12 volts, and the green wire, which is the startup wire. We connect that to ground basically. So this one again, we have a connection to the metal case. So as long as we don't let these two physically touch each other, you would think, well, the ground is isolated because there's no connection from here to here, obviously. But these power supplies are mains powered and they have a mains connection. Now, is the ground here connected to the metal case? Yes, it is. And how about the other one? Yes, it is. So if we connect mains leads to these and plug them both into the mains, effectively via the earth wire through one mains lead, the earth wiring in your main socket in your house or your office to the other one, they will be connected together. Okay, we will actually create a short between the two cases, which is the two sets of black wires, the two grounds, via the mains wiring. Now, we could disconnect the ground lead, the earth lead to the power supplies, but really that is not a very good idea. It's not a safe thing to do. We really want our power supplies to be earthed or grounded. But what we can do is disconnect the black wires, the ground on one of our power supplies from the chassis, from the metal frame. We only need to do it on one of them, but you know, I'll probably actually do it on both so that they are floating, they're isolated. That's also rather useful with bench power supplies. So let's see if we can disconnect this, the black wires, from the safety ground, but still leave the safety ground connected to our power supply. Here is one of the power supplies. Let's look to see how the black wires connect to the chassis ground. Well, this is the power supply. We can see this is the high voltage side and the low voltage side. So it's the ground from here on the black wires we want to disconnect from the chassis because that's how it's connecting to the safety ground. You can see we have some areas here and here. These are bolted to the metalwork, and we have some areas here and here, and these are bolted to the metalwork. And that's how it's making the connection from our output ground to the safety ground. And that's where we need to effectively cut the connection. These ones, we want to leave these intact. This is safety ground, and they connect to a few capacitors. In fact, probably only the one capacitor actually here. But we can leave those. We want to isolate these basically. I think the best way to do this is to cut the track with a Dremel like so, and here like so. What do we have here? We have a couple of resistors here, yeah. So really this area we want to cut away so this is not connected to the chassis. And then we need to run some wires to make sure that this track is still connecting to this track. This looks like it doesn't go there anyway, actually. It looks like a gap, but we want to make sure that it is all connected together as it is. So let's get the Dremel out and let's do a little bit of work and then a little bit of soldering. I've modified this one, so you can see I cut the track around here where this attaches to the chassis on both sides. We'll have to just check to make sure it's no longer touching the metalwork. And then I've connected these tracks all back together. So we can see we have a connection to here onto this track. But we don't have any connection anymore to here or to here. Another way to do this, you could put a plastic shim on here and then use a nylon bolt. That would also do the same job if you don't fancy carving up the PCB, but this is the way I chose to do it. Let's bolt this back into the case and let's see if we actually have isolated. And here we have it. So we still have, if we look, from the ground, the safety ground, to the metal chassis, we have a safety ground. But if we look from the output, the negative, the 0 volts, the black wires, we no longer have a ground. So we've isolated the output on this power supply from ground, but we still have safety ground, which is exactly what we wanted. Let's have a quick look at the other one and then do the same. This is the other power supply, much larger transformer. This is obviously a higher rated power supply. I would suggest you try and use 2 power supplies of similar rating, and also looking inside the kind of the quality of the build. If you find 2 with similar sized transformers, they're probably a good match for each other. But for our experimentation, these 2 will be just fine. Once again, this is the high voltage side of the circuit. You can see the gap here. So this isolates the high voltage from the low voltage. And again, this is where all the black wires come in, and we can see it's attached to the ground here. And if I can just get us out a little bit further, it's attached the same here. So once again, I'll cut away this section with the Dremel and then just make sure that we have a connection where we should have. There's nothing actually soldered here, by the way. I'm just checking. But I'll just make sure we have a connection from here again to this track and up the other side. This is the second one. I've made a little bit of a mess of this. I was struggling to do it, and then I realized I could cut some zip ties and get the board out much easier. But again, this is where the safety ground was here, and we've now isolated it from here. Okay, and we can see it came across here. It went into this area. So it's isolated from here. And the same with this one. You can just double check. Isolated. Now, this track here, which I cut, but I didn't actually cut. If we just go onto here, that's fine, we have continuity. This one here should connect to this side. And in fact, it's still, no it doesn't, so I need to put a wire. Also, it should connect to here. This is where all the black wires are, okay. So we can see from here, we actually have a connection to here. So I don't really need to run a wire across there. There's obviously some other path on the PCB into this area, all the way up here you can see. So that's fine. From here, there isn't a connection to this one, so I'll just run a wire from there to there, and then this one's ready to try. There's no reason why you couldn't put a wire across from there to there if you wanted to, by the way. And we have it, just one short wire on this one. So, from this track, connected. So we have the ground where we want it. This one's also ready to put back together, so let's do that. And then again, we'll just check if we have safety ground, but we have an isolated output ground. From safety ground then, to the chassis, yeah, we have it. From the black wires, any of the black wires, doesn't matter which ones, to the chassis, we don't have a connection anymore. So that's exactly what we wanted. Let's try another one. Yeah, that's good. Let's try to connect our two ATX power supplies in series now to get 24 volts. First of all, we need to make sure we can start the power supplies. So the way to do this is to connect the green wire to one of the black wires, doesn't matter which one. As I'm not going to be using these as ATX power supplies anymore, I'll just cut these two wires and connect them together. This will make the ATX power supply automatically start now when we apply mains power to it. Wasn't very well soldered, was it? Okay. A bit more. Try again. Looking better. So we have that one. We'll do the same with the other one. So again, we'll connect the green wire to one of the black wires. There we have that one. Now we need to connect the 12 volts from one of them. Let's go with this one. To the black wires, the ground on the other one. Once again, I will just chop some of these wires. And we can do the same here with these two black ones. And there we have it. So the black wires on here, this will be ground. This will be 12 volts. And the yellow wires on this one will be 24 volts. We have this ready to try then. Let's connect it up and let's see what we get out of it. I have this plugged into the mains, both of them, not switched on at the moment. Let's check them before we power these up. So if we measure the resistance from ground on this power supply to ground on the other power supply, we shouldn't have a short. Well, in actual fact, we read 49 ohms, so we do read a resistance. You know, I think the reason for that is because across the 12 volts output here, we have a 49 ohm resistor. Let's just prove it. So we'll just disconnect the connection between the two power supplies for a moment. Okay. Do I have 49 ohms from ground to 12 volts on this power supply? Let's see. Yeah, I do. So that resistance is on the power supply anyway. That really isn't a problem. Let's connect this back to the ground on the other one. And while we're at it, actually, let's just measure the resistance on this one. So ground on this one, 12 volts. Well, that's reading higher, a couple of 100 ohms. Let's connect this back together. Okay, we've linked them together again. We need to measure the voltage from ground on this power supply. Okay, we're in there. And we're going to go to 12 volts on this power supply. We're in there. Now we're seeing about 260 ohms, so that's the 50 ohms and the 210 roughly that we had. Okay, I'm happy with that. Shall we just switch this on and see what happens? Yeah, let's have a look. Nothing spectacular, I hope, unless it just makes a good video. We have 24 volts. So we clearly have the 24 volts coming out of here. This is what we want to feed into our PCBWay project. Now, I think we may have to make one modification just before we do that. Let's look at the schematic again on PCBWay.com. You can see this op amp is sensing the output voltage as we discussed before. It's comparing it with the voltage here. So by adjusting this adjustment, we set the voltage at which this turns on. Once the inverting input goes above the non-inverting input, the voltage here will actually go down. Okay, and that turns the PNP transistor on this way, okay, and powers the relay. Now you'll see this relay, which is a 12-volt relay, has a 100 to 180 ohm resistor here. The reason being is because this has an 18-volt supply. So this is to prevent the full 18 volts appearing across the relay. Now we've changed this, so we now have 12 volts here and 24 volts here. Because of that, the relay, when the transistor turns on, will have 12 volts. So we need to short this resistor out. We don't need it anymore. So let's do that, and then let's power up our PCBWay power supply, and let's see if we can set the bypass adjust so that when the output voltage gets near to 12 volts, it switches the input voltage from 12 to 24. We'll know it happens because we'll hear the relay switch. I have this ready to go to try. I'll just show you how it's connected up. So from this power supply, this is the 0 to 12 if you like. This is the one that gives the 24. So ground on this, one of the black wires, you can see is connecting to the negative on the in. It also has a crocodile clip on it which goes to my black meter probe. So that's the ground. From the same power supply, the 12 volt out connects to the 0 volts on the other one. And also from this power supply on this red wire, this is 12 volts from this one going to the relay. Okay, that relay contact is the normally closed one. So until the relay triggers, that 12 volts comes down this yellow wire to here. The other one, the violet wire you see here, if we just follow it, goes to the 12 volts on the other one. So this is the 24 volts connection, okay? So the other thing I've done is put two 12 volt light bulbs in series so we can put up to 24 volts on the output. I don't think we'll get quite 24 because there'll be a little bit of loss in through the transistor basically. But that's what we have. I've turned the voltage fairly low down at the moment. Let's switch this on and let's see what it does. Well, you probably noticed the current limit light flashed once. Both power supplies are running. You may hear the fans, but I can show you. So this is the output from the first one, the 12 volts. We go on to 12 volts. And we have 11.3, so that's running. We go to the output from the second one, the purple wire, and we have 23.18. So we definitely have the supply. On the voltage in, we have 11.3. But the light bulbs are not lighting up. Nothing. Okay, what voltage do we have on the output? Well, we have almost nothing, 0.36. We can also monitor that on the output from the transistor, which is probably easier. There, okay. Let's adjust the output voltage. Well, it went to 0 and back to 0.36, okay. There's a current limit on. Well, it goes to 0 and back to 0.36. So something's stopping the output voltage going above 0.36. What's coming into our output transistor? 12 on the base, 1.1. Okay, what's on the emitter? 0.4, yeah, so we have a 0.6 voltage drop, that's about correct. So if we go to the base, this voltage should adjust. Let's see. Transistor's cold, by the way. 1.1. And it's not adjusting, I'm altering the voltage setting. So for some reason, the drive to the transistor isn't changing. Let's have a look at the schematic. Here's the schematic then. So basically, the voltage on here isn't increasing. So we need to look at the base of T3 to see if that varies when we alter the voltage adjust, and we need to have a look around T2 as well, and pin 9 on IC2. Let's take a look. Base of the driver transistor then. Well, that has 10 volts. Collector 1 point something, that's going to the base of the output. Emitter should be about 11 volts. Yeah, 11.2. This ultimately comes from pin 9 on here. And that's strange. When I touch that for a moment, the current limit comes on. Yeah, that's not adjusting. Okay, so we seem to have upset this. This was previously working when I had 15 and 30 volts coming into it. I think the first thing I'll try is I'll reconnect my power supply and make sure this is still working, that something hasn't gone wrong with it. To do that, I'll just remove this wire link on the relay again. I'll connect my power supply, 15 and 30 volts. So let's see if it's working. I have my bench power supply set up. I'll just show you. So the red wire, this has 15 volts. The yellow wire has 30 volts. This is how we previously tested this PCBWay power supply module. Let's try it again to see if it's still working. So we'll connect the ground from the power supply. This is this one. We'll connect the red wire into the relay. This is the 15 volt. And we can connect the violet wire from the power supply. This is the 30 volt. So we have this ready to test again. I'll just put the light bulbs where we can see them. There we go. Let's switch the power supply on and let's see what it does now. Well, we have the overcurrent and we have the filaments lighting up now. Yeah, I'm actually adjusting the current. We can adjust the voltage, turn the current limit off. So our PCBWay power supply unit works fine from 15 volts and 30 volts as it was designed to do, but it doesn't work with the plus 12 and 24 volts. So before we can continue and figure out how to modify this further to work 3 ATX power supplies, and we're going to switch them with the green wires, we need to work out why it doesn't work on 12 volts when it does on 15 volts. And that, my friends, is going to be another story. So this one's plenty long and we've learned quite a lot about ATX power supplies and how to run them in series. Next one, I think, will be by next week at the latest. Let's see why our power supply doesn't run on 12 volts. I hope you did enjoy that one, guys. And once again, thank you to PCBWay, who kindly sponsor these videos, which allows me to spend time doing this sort of thing for you. We can all learn a lot, I am sure, from it. So until next time on Learn Electronics Repair, ciao for now, guys.